Even if you forget, you have it with you.
Okay. Thank you very much, Jan, for being here. Very much for listener from home also. So speaker of today is Jan Zavodnik. He was postdoc here in CISA until last year, basically, and is now at the University of Ljubljana. Please, Jan, you can start.
Roberto, thank you for introduction and for inviting me here. Yeah, I will today talk about geometric soft mounts in heat structures. So how you can basically use them or program them maybe to morph, to change shape, or even to explain propulsion in cell movement. So first, something about my background. I did my PhD here actually in Ljubljana at Faculty of Mechanical Engineering for nonlinear mechanics with Professor Miha Brojan as my mentor. And after the postdoc, I went back there and I'm doing further work. So first, how I got interested in mechanics of slender structures of thin shells, beam rods, is by doing wrinkling. So wrinkling, I was for my PhD analyzing how structures, particularly curved ones, wrinkle at the surface. So when you have a gray is the shell, thin shell, inside you have soft material, and then you apply or reduce pressure inside, you get compressive forces in the shell outside. And basically, you get localized wrinkling on the surface of the shell, which are called dimples or wrinkles. And the interesting thing is that they distribute themselves by the rules of crystals. So you can basically make parallels with crystal theory and actually also compute the distribution by the rules. So after the PhD, I continued my work on shell mechanics, basically with Professor Antonio De Simone here for 1.5 years in CISA. So, and I will show you what we did together. We basically branched out a lot. So basically, but the common denominator is the surface or are the surfaces. So the classical surfaces are shells like this, or the meta surfaces that I will show today mostly. And the focus was on application and computation and understanding what's happening, because we wanted to see how you can basically get soft modes in these surfaces so they can be heavily deformed in order to obtain some applications. For example, braided meshes are kind of surfaces, although they are not really surfaces, right? They can be modeled as surfaces. And the other class that we will focus on are the pellicle surfaces. Those are inspired by biology, by these micro swimmers. They can rapidly deform and swim in that way. And they inspire, for example, different metamaterials that can morph. Or you can explain flagellar mechanics, so how these microorganisms can swim and have a large deformation and allow them to propel themselves. So the main thing, so we start by classical surfaces. How are they different from these meta surfaces, basically? So a classical shell is basically a 3D solid material, but because it's very thin, you can, like Roberto, you explained already, you can basically use modular reduction and analyze them as mid-surface with effective stretching and bending stiffnesses or penalties on the energy, if you like. You have a reference map from 2D to 3D. And so for the reference surface, reference shell, and the metric, and the curvature, or the second fundamental form. These are your properties, geometrical of the surface. And then when you load the surface, you deform it, you get another map with another metric, another curvature. And then you penalize, you call this stretching strain, the difference of metrics tells you how much you stretch the surface, and the difference of second fundamental forms or curvatures give you the bending strain somehow. And they are non-evenly penalized in surfaces or in shells with thickness scaling with h for the membrane strains and with h cubed for the bending strain. So meaning that you can easily curve them, because you will, for thin surfaces with small h, you will cause small energetic penalty, but for stretching have large penalty. Now you could say, okay, then I will just, if I want a large deformation, I will just keep bending them. But the thing is that these fundamental forms are connected, right? So again, it's Gauss theory says that a part of the second fundamental form, the Gaussian curvature, is connected to another part or mode of the first fundamental form. This relation is very complex in Ricci calculus, but in Cartan calculus, basically it gets more nicer form that is more informative. I will make a comment on this later. But the thing is that if you form your surface in the right way, it is quite difficult to deform, which is nice, right? So you produce a curved sheet, then or car, and when it crashes, it doesn't smash you so much if it was flat, right? But it's problematic for if you want large deformations, you want to produce 3D objects from 2D sheets. Then inevitably you will encounter buckling or wrinkling, loss of stability if you want to produce shape like this. So the middle one, which is not isometric from a flat plate, you will get wrinkles or buckling. And then how do we avoid this? We find soft deformation modes or surfaces which have soft modes, and they can easily change the metric. And then we can basically bend them a lot and then excite the easy changing metric part, let's say. So a solution is maybe wrinkling-induced, where you intentionally allow or produce wrinkles so that you alleviate membrane strains, or buckling as well. Buckle-induced is called, or wrinkle-induced, excuse me. Or you can use kirigami principles, where you basically, for stretching such a surface, basically you bend the folds, and then this is energetically cheap. Or you use kirigami, where you have cuts, which also allow you to introduce soft mode. But you also have two different principles that we will focus on today: Chebyshev nets and pellicle surfaces. And they also have soft modes, because these meshes can basically change the angle between the families of the fibers without any large cost. While these surfaces, they have rod-like structures on the surface, they can basically slide, and then with that you can also alleviate stresses and reduce the cost of large deformations. So then we go back to our Cartan differential geometry. Basically, in some sense, we used these rather than Ricci calculus, because it turns out it gives you a bit more information. It's more physical than Ricci calculus, which is nice but heavy to control. So basically, what you do is, when you have your map of your surface, usually we work with a natural tangent basis. So you compute your tangent basis, you do everything inside your vector fields, you write them as a linear commutation and so on. But here, first, before that, we construct an orthonormal basis. So A and B are this new basis, and okay, you have the normal as well. And this orthogonalization process can be stored as a matrix on the natural tangent basis. And this allows you to use directional derivatives instead of partial derivatives on the surface. And this principle has nice properties that the Gauss theorem is now quite elegantly written and has better geometric meaning. But also, if you compute a second fundamental form in this basis, you basically get the curvatures, the normal curvature and the torsion of the curves that this basis represents. So these A and B basis vectors basically point in the normal directions of the curves, and you basically get second fundamental forms. A form is basically just curvature of these curves, and which is very nice actually. And also the elastic energy of such structure. So a shell, as we said before, is composed traditionally from, it looks like this, as we described before, penalty on membrane strengths, on bending strengths. In Ricci calculus, it looks terrible. I mean, terrible. It's, if you would to write it explicitly, it would be a really long expression, but then if you use Cretan-based representation, the explicit expression is just like this, so it's easier to think of, handle, and reason with it. So for discretization of the surfaces, for numerical computations, we use spectral method, spectral collocation method. To be precise, is basically you present your function of your domain as a sum, weighted sum of Fourier modes. But instead of using, the approach is a bit different. Basically, you are working here with values of the function at the collocation points, which are evenly spaced. And then when you want to compute derivative, you just multiply by a derivation matrix, which assumes the underlying approximation by the Fourier modes. So you get a very accurate result that way. The only downside is that this method works for smooth functions, but shells usually give smooth results, so this is quite okay. And the domain cannot be too wild, let's say. So, and then so this is for periodic domains, but for this for finite domains you use Chebyshev spectral collocation with Chebyshev functions as the basis. Then 2D is just a composition or like you just use both bases, and you can map 2D to a cylinder like this. Now the underlying assumption is smooth, just the plotting it looks rugged, so let's say. And the nice property is that with small number of edge points, let's say in a shell like this converges very rapidly to the solution. So the solid lines are the spectral collocation discretization on this benchmark example, and the finite elements are these dashed points. So for highly nonlinear problems, this is very nice because you want to minimize the number of degrees of freedom, and you can do it this way. Okay, so and then to seek equilibrium, we minimize the energy directly. So you compute the energy of your system, of your state, then the gradient, which you seek to be zero, to be at the bottom or to be at the fixed point, and the Hessian. And then with these two, you take your Newton step from a start. But so here is the energy landscape. This energy provides basically safeguards, and it tells you how far along this line that the Newton method would give you, how far you have to go to reduce the energy, because the classical Newton rhapsody can quickly go to the saddle point, while this energy minimization basically goes to at least locally stable energy minimum. So for problems like this is extremely useful because you get nowhere with classical methods. So you just minimize the energy, and it's actually better, even though it's conceptually easier, maybe. Yeah, so now we come to the geometry of the braided meshes, our first soft mode. Turns out you can model this fiber by fiber, but here we'll focus on the envelope surface approach, where you basically assume you have this envelope surface, and the curves on the surface that you define, or basically the vector field of tangents that you define, those are your fibers. And you can define your tangent fields like this, like a rotation of the Cartan basis, as we described before. And then in the deformed configuration, again, you just make a derivative, directional derivative with respect to the old tangent directions, and you get the new tangents. And then you have, okay, you can compute the normal. You have to make sure that you assume the lengths of these fibers doesn't change, right? So the dot products have to be equal to 1 at all times, and the mixed dot product gives you the cosine of the angle between the fiber families. So you get the basically field gamma of the angle field on the surface. And it actually turns out, so this is the deformation that happens. So this is the soft mode in action. When you deform this structure, you basically change the angle. And this is the soft mode because this is quite easy to do. And actually, the Gauss theory gives you the relation between the Gaussian curvature and this angle field gamma. And you can basically, for example, for a hemisphere, you can compute what this gamma angle field should be on the surface. And you can compute basically, if you want to produce hemisphere like this, you can compute that the starting domain should be like this, and you can also compute how much the angle should change and so on. But computationally, we have to also define the elastic energy of such a structure. And basically, you go again to write the energy of the individual rods on the surface or elastic fibers. You say the out-of-plane deformation, bending strain is just a change of the curvature of the surface in the direction of the fiber. The in-plane bending strain, this is a new thing. This is classically not present in anisotropic materials. So you penalize the bending of these fibers in plane. You penalize the twisting of the surface in the direction of the fiber, plus you, to describe the twisting strains of the rod, you add additional degree of freedom of twisting, because you assume, right, these fibers can also rotate relatively to the surface. You put everything together and then integrate through the fiber and sum up all your fibers. This is for one family of fibers, then you do the same for the other family. But you can actually translate this integration and summation to the envelope surface. So you basically get a material law for envelope surface with fibers in it. And as I said before, it's different from standard anisotropic material laws because it basically penalizes geodesic curvature of these fibers or their change as well. So this is the experiment we made. We took a braided mesh, fixed it at both ends, so the ends stay like circular, and then we applied axial force and observed how it bends. Basically, we moved these points towards each other and looked at the reactive force. So this is the reactive force in relation to the displacement that we impose. And first, maybe focus on the dots, the experiment. So you just put it in the machine, you put the ends together, you observe that when you deform and when you remove deformation or load, you get different force responses. This is basically due to friction probably between the fibers. But then you can do the experiment in another way. You deform a bit, stop, tap on the sample to alleviate friction, and then you get these stars, which are closer to the green simulation line, if you see, right? And then we have two simulations. The circles, the red circles represent the simulation where we do not allow relaxation the fibers. Meaning, fibers cannot rotate with respect to the surface, but the green one shows you when we allow partial relaxation, meaning there is some rotation of the fibers relative to the surface. And this one works better. The problem is we don't yet have the law to tell you how much relaxation you should give to the simulation. So this is the missing part still. Okay, then you can see the bending energy is focused here on the edges, while the twisting is on the top or the middle of the sample. And we observe brassiere effect, so the oval or like ovalization of the cross section as well. This is what emerges in experiments here, you see, and also in simulations. So this is at least one metric. It tells you the simulation at least works, or at least qualitatively right. Okay, so with this established, we can move on to the other case, the pellicle surfaces, which in my opinion are more interesting. So we said, basically, you can again model them by rod, right? You can get a good estimations, modeling from that, but more robustly, you can again assume a surface with lines or like curves on it, and then when the lines slide relative to each other, you get metric change like this. So again, this is the Gauss formula, the relation between the metric and the Gaussian curvature, which you can again solve analytically even for constant Gaussian curvature, and obtain this sliding that causes constant curvature. So this is in collaboration with Marino Arroyo from Barcelona. And what we can see basically is, or we can define a forward problem. So you put some sliding field in the surface, and then what shape should you expect? This is what we are trying to simulate, for example. So this is the starting configuration, the metric and the curvature for this plate or for the cylinder. This, and then you apply some gamma, some sliding. What will be the curvature, right? So you again write the bending energy for particular rods, minimize this subject to the constraint, the matrix, the first fundamental form has to be the right shape and the boundary conditions, and you basically get this. So this piece of this plate becomes curved here as well with a negative Gaussian function. Good, and then you can play with it for application purposes. We can see or analyze whether this cylinder can be rotated for like a small swimmer or something like that, right? Whether we can whether this sliding metric can allow this deformation without any other strains that would be heavily penalized. And it turns out this works. So you can here observe the angle of the rotation of this cylinder, and you get red is the stretching energy. It's zero everywhere, so this principle works, which is nice. But you get a rise of the bending energy and bending moment that is needed to rotate this. So this is because you are changing the curvature in plane, geodesic curvature of these rods. So they are bending, so you need energy for that. Then we hope that we can make the parameters such that this hill here of the energy will be small enough that this can actually be done, for example. So then you can produce swimmers and feeders and everything like this. So yeah. And there is an interesting inverse problem. So given you want to produce like a sphere like this with holes at the ends, what shape should you start with of your rods? You want to have a sheet or a cylinder of rods. What should be the size of this sheet that you will deform into this shape. So that's why it's an inverse problem. And how to solve it is very interesting. You basically draw parallel lines on the surface, and then you unslide these lines to make it cylindrical again, yeah. And then you produce cylinder like this, and then you do the reverse, you slide it, and you get reversely this shape. The interesting thing is that there are many ways to do it, right? You can the same shape, right, but different lines. And then when you unslide for the same amount or remove Gaussian curvature, you get this shape. Now, luckily, this can be trivially unslided, let's say, to a longer cylinder like this, right? With a constant sliding field. But there are shapes where you can draw these lines, but you cannot unslide it because it has no hole here. There is no way, right? Nothing will change if you unslide it. And there are also shapes where you cannot draw parallel lines on them, usually due to some singularities or something like that. So it's not universal, but it works for many different shapes. Okay, then here are some examples. You can flatten hemispheres of different sizes, then a saddle, and then a canal like this. And here is actually a prototype that was made by Marino Arroyo, Noceli, and De Simone. So these things actually work. You can actually do it physically. All right, and now we move to a very interesting domain, the last one, of flagellar axonemes. So it turns out that also the axoneme with which these microorganisms swim, they're also composed of microtubules, microtubule pairs to be exact. So this is a pair, and it can slide relative to this pair out of this plane, out of the cross section, and there are motors between that regulate this sliding. And that is how this thing is reshaped. It was shown by Irene, former PhD student of Antonia, that she devised a very complex chemical model, how these motors work, and it can be reduced basically to the fact that this force that is generated is proportional to the rate of sliding that is already happening. And then you have nonlinear stopping term. And if you assume that this force in the simplest case goes to a spring, so it's used for deformation of a spring and for drag in the water or fluid, then you get a limit cycle, basically self-generated oscillations like this, right? And basically you get beating. So this could be an explanation why you have beating in these microorganisms and propulsion. Now, if you observe closely, there is a non-planarity of the movement going on here. And it is interesting to ask yourself, why does this happen? Why the out-of-plane movement is not the in-plane movement more, let's say, energetically better? And so the torsion of the curve is the measurement of the out-of-planarness, let's say. Is it due to twist? So, or due to change of bending plane, meaning twisting means, right, that the structure around the curve rotates, while the change of bending plane, just the structure is not rotating, it just bends in a different direction, right? And how do we measure can we devise a model to measure the internal activity and motor force inside? It turns out, yes, we can do it. Basically, we can use the model reduction from the surface to a rod. So we define the center line, the blue curve here, which is dependent on the S parameter, or here in the sketch U parameter. And then around it, we built this orange shell representing the microtubules. with radius r in the direction of d1, director 2, and there is also tilt present, tilt of this cross section. And you have to apply again the loss of the sliding metric to this surface as well. And from the first constraint, so you say, okay, this length cannot increase or decrease of these tubes, macrotubules. You get directly the relation that the shrinkage of this structure is proportional with, like this, to the twist omega. So omega is the twist, lambda is the shrinkage. And if this center line curves with K1, you have to tilt by U1 prime, and the same in the second direction. You have to tilt if you want to bend the structure. And the second condition gives you that when you twist, you have to increase the radius, like you see here. And then the third one, the sliding, it gives you that the sliding has three modes. The constant mode along the circumference. So when you apply a twist, you get constant sliding along the circumference, and then sine and cosine modes. This corresponds to bending, those two. So this is twisting, and these are bending in the two directions. So this is now just kinematics, and then you can also write the potential energy of these microtubules around with respect to the parameters of the center line. So we want to reduce everything to a rod model. So you introduce out of plane bending stiffness, penalty to the microtubules. So out of plane bending, then G is the in plane bending stiffness of these rods, or sorry, these microtubules. Then we have twisting stiffness because they twist, and then intra-fiber bending when you, in case the microtubules would bend like this, but this is negligible. Usually it doesn't, it's a small penalty, so we neglect it. So then you put everything in the kinematics, in the energy, and we only reduce, so we leave only the lower order terms, so linear and mostly quadratic, or at most quadratic terms, and we get this energy dependent on the properties of the center line only, although they consider they are derived from the bending stiffnesses of the rods outside. You first notice that the bending is independent of the direction of bending. So it's the same way, if you bend in one way, it's the same as you bend in the other direction. But the most or more interesting thing is that you get this negative term, provided T plus G is larger than T, which is true. For our shapes, this is mostly true. So you get a destabilizing term. Why does it arise? It's actually quite intuitive. So, okay, you get this classical bending term. The more curvature you apply, the larger the energy. Twisting term, the more you twist, the more energy. But there is this mixed term. If you bend the structure with no twists, you have some rise of energy. But if you first twist the structure, right, like this, you use some, you input some energy, but then if you try to bend it, you will need less energy than without the twist. And this negative term is basically due to this. So the fibers under the angle, they are easier to bend. That's it. And the last term is just geodesic curvature due to twisting. It's not so important. So basically you can do a test. Let's apply a curvature to the center line, undirected, in some direction, whatever, and observe if twist is energetically favorable or not. If the curvature is small, then the minimum of energy is with zero twist. But if the curvature becomes larger and larger, then you quickly lose stability of this solution with zero twist. And if we were to have a nonlinear, if we were to leave nonlinear terms, we would find a non-trivial equilibrium of twist. So somewhere in between, when you increase curvature, the structure will spontaneously twist as well, due to this concept or due to this mechanism here. And in simulations, actually, it turns out this is true. These are the simulations, not with the rod model, but with the surface model. So when you apply the curvature to the center line, you basically get the twisting as well. So basically, you get something like this. The ends meet like this, right? And conversely, if you apply twisting, you get bending as well, like this, which is quite interesting in non-standard model, basically. And then there is a question, as I said, is this torsion from bending or from bending plane change, or is it from twist? So this is a kinematic relation. The torsion of a curve, we said, is a measure of non-planarness of the curve. So when you bend, you have a donut, you twist one end. Will you get this situation? The torsion that you observe, is it coming from change of bending plane, like this? Look at the green fiber. First, it's bent around longer direction, let's say, then gradually the bending plane changes. This is one situation. So the bending direction or axis is this blue curve here, right? Or is the situation the opposite? Again, you lift one end, and does the fiber stay bent around the same axis, but you additionally get twisting in the structure. So these are the two extremes that you can observe. We put both into the energy again, and we figure out that for small deformations, it is optimal to just change the bending plane when you curve, right, or when you change the curvature. It's better to just change the bending plane than to twist, because twisting introduces additional energy into the system, like this, with this term. This is in line with this paper, but contrary to experiments by Flagellar in Nature Physics from last year, which is interesting, right? In real structures, they observe this phenomenon, the lower one. And this is actually energetically favorable for large K and omega when this term starts to work. It's actually better to twist as well. And maybe this is the explanation why in experiments they actually see this. By the way, if you were to perform an experiment with a standard rod, let's say a hose, you would observe this situation if you were to draw with a marker a line, and then when you lift, basically it turns, and there is no twist involved. But like a strip, if you lift it, it has no other way but to introduce twist, because it cannot change the bending plane around it, which it bends, because of the difference of stiffnesses, right? So of one or the other axis. All right. So the other question is, so okay, given that we observe this twist as well in experiments, in the paper they said, okay, this is probably because of the bridge. Bridge meaning that there is a place where two microtubules are fixed rigidly and they cannot slide relative to each other. So there is a place that with no sliding here between two fibers. And when we assume that, remember we have three modes of sliding in the structure: constant, sine, and cosine. Constant with respect to v coordinate around here. Then when we fixed one, then we only are left with this constraint so that tilting in one direction is the same as twisting, or minus the same as twisting. So this is this mode, and then the other mode which says you only bend without any twisting. So these are the two possibilities. And then, yeah, we remember that when you bend the structure, you have to tilt the cross section as well. Then test case. Again, we apply curvature to the mid-center line. Undirected, meaning, so, okay, we apply, and then alpha is the cosine alpha goes to K1 mode, sine alpha goes to bending in the other direction. And then we put this into the energy and observe which is energetically more optimal, the red one or the blue one. It turns out, again, for small deformations, it is energetically more favorable to just bend like this without any twisting. So this is the bending plane around which it bends. And the green one, the green stripe, is the place of no sliding. But again, due to the nonlinear term with minus for larger deformations, the minimizer is alpha is pi over 2. And you get the blue mode, which is optimal, meaning deformation shape looks like this. So you have simultaneous twisting and bending in the other direction. And this is what is also something like this is observed in experiments. So this could be an explanation. Good. And so finally, I want to introduce the immediate goal. We want to continue with this and then maybe apply this theory to the real results. So these are the measurements actually. And then we want to actually feed the mechanical model to these experiments and recover internal sliding to be able to assess motor activity, because there is a flood of models how these internal motors behave, and we want to actually measure that and assess how they actually work, which theory is correct, which assumptions are correct. The problem is that, okay, you can fit the model to the center lines that are measured, but you have to know the boundary conditions here. Here they are free, so it rotates. It's probably not so correct. Then should we regularize with elasticity, viscous drag, and what to do with bending loss of stability is also a question. But I think that this model gives us good hope that we can do it with the bridge analysis. We don't need actually a regularization. We only need to apply geometry and we can get the data. So this is kind of a summary of what we went through. So yeah, thank you very much.
Thank you very much. Thank you, Jan. I have a lot of questions and curiosities, but if there are other questions from here or from online, people, otherwise I can start asking something related to the numerics at the beginning, because you mentioned the spectral methods. That seems very interesting because I have done also some computations on surfaces, and I know it's quite difficult. So I was just wondering if you could provide some more details. And for example, you are solving the problem, and you are basically solving the problem numerically in the 2D space, like the ones in which you write the curvilinear coordinates, right? And so, okay. So is this working? Basically, can it work for any kind of problem, for any kind of shell you want, and it is time dependent or not time dependent? It's just you have the energy, you can minimize the energy through this method. It's based on like finite elements. Are you reading weak forms? I'm just wondering how it works because I do not know.
It's just basically you just take. You have your values of your function at discrete nodes, yeah. Let's call them.
Yes.
And basically, because you have the underlying approximation by global functions, basically you can
Global functions.
Yeah, so those are global approximation functions. Yeah. So basically you can make derivatives in these points by just multiplying with these derivation matrices. They assume underlying approximation, so you get a really correct, really accurate computation of derivatives in your points. So basically discretize the problem. You basically write the energy with respect to your vector of function values on the grid. Okay. So basically you get...
So you start from an initial guess and then you minimize the energy just... Okay.
You basically compute for your points on the grid, you have function values, and then you basically, so this is your vector of discrete values at the nodes, and then you compute the potential energy of these discrete values.
You just minimize it.
Yeah, and then you just minimize, you compute the gradient, the Hessian, then just put into the minimizer and just go, and it goes very robustly. Yeah, so that's the...
You perform it with MATLAB?
Yeah.
Or so everything can be done with MATLAB?
Yeah. And the beauty is also that this discretization is very, I would say, it demands very few degrees of freedom.
And that was another question, because it seems like it was not so computational heavy.
Yeah. That is also the beauty. That's why I went for this method rather than...
Is there a drawback somewhere, or...?
The drawback, it is. The drawback is that you have to start from a rectangular domain. So
in any case...
Yeah, I mean, you can then map it to something else, but you cannot have holes in it, let's say, or something like that. That is the drawback. So it's not so general, but for my examples, it was enough, right? But so as long as you don't have holes in it, it works, right?
And for the simulation with the sphere, did you use like the standard spherical coordinate parametrization? Because or you had like some, because I remember maybe with this parametrization you may have some problems of at some boundary. I don't remember exactly some.
For this one, or
for the wrinkle one, maybe the first one that you have shown.
Yeah. Basically, the wrinkled one. Does it work here? Yeah. This one basically is a bit different.
It's a whole sphere, or
Here I used spherical harmonic functions as underlying.
So for the specific geometry,
I mean, this was very difficult problems, because if you don't use spherical harmonics, you get problems at the poles because you have singularities there.
That's what I'm.
Yeah. So, and then spherical harmonics functions, they handle this automatically, so you don't have any problems because of that. Yeah, right. But otherwise, you can get a lot of geometries from this combination from a combination of Chebyshev times Fourier, you get all the cylindrical shapes, however long you want, however tilted. You just have, I mean, if you can apply smooth map to get it, then you can use it, no problem. Or for this geometry, you can use Chebyshev times Chebyshev, and it works very nicely. So, yeah.
Thank you.
Yeah, you're welcome.
Sorry,
we have a paper coming out about the method, how to use it for mechanics, but it's not quite yet finished. So
focus on the numerics side.
So hope it's finished quickly, so the details can be.
Okay. Another question I had was concerning the fact that you have shown the classical shape model, I would say. I don't know if it's maybe something related to Coiter's model, probably, because you have, I guess you are assuming like very small thickness, so you have not shearing in this way exactly. And then you showed us the model in which you start from like a ruled surface, so you start from the curves and then extend in a sense along the surfaces. And I was wondering whether, since the standard model is for isotropic materials generally, and you use the the second model for modeling also anisotropic behaviors, if they can be connected in some way, or if the second model is just uses just some intuition in the sense that, okay, I know that this can be penalized, so I put an energy, or if you have some intuition that it can be, reduced from the three-dimensional case or something similar.
Yeah, basically it's there is a connection basically between anisotropic models and this model. Well, this is more built on intuition. Basically,
because, there are like lines, so you penalize certain direction of such lines, and okay.
Yeah, so this is basically assuming these curves on the surface are Kirchhoff rods. So each one has its own bending rigidity in the for bending and then for twisting. You can also generalize a bit, remove the constraints and give here stretching strains as well.
Yes.
Instead of constraints. That's fine, it works. And if you do that, actually you get the same type of model that is an anisotropic model for shells, except this one has an extra penalization on the in-plane bending of the fibers, and the classical ones don't have that. This is just, basically from this kind of intuition, you basically build a model that was phenomenologically chosen, I guess. Yeah.
Thank you.
Yeah,
You're welcome. There are no other questions. Maybe we can thank the speaker again. Thank you. Yeah. Thank you very much all, and thank you all from home.